Elastic properties of solids. So in this video we're going to address the issue of the amount of deformation we can get on an object when we apply a force per unit area. So all objects are deformable to some extent, and the question is whether this deformation is reversible or irreversible. So that is to say, can we go back to the initial condition of the object? Okay, so we have the cause of the deformation, that is stress, denoted by sigma. It's the external force acting on an object per cross-sectional area. For example, you can see here we apply a force. Force divided by the cross-sectional area of this bar is basically our stress. Now, the result is the strain. So it's the measure of degree of deformation. For example, in this case, you can see that during the application of this force, this object which is clamped on the other side elongates by an amount delta L. So delta L divided by the initial length of the object is a measure of the amount of deformation that is called strain. So we denote strain by epsilon. And all objects have this very fundamental stress-strain relationship. Now, since stress sigma is force per unit area, it has the unit of pressure. So, for example, this is typically in megapascals. And strain is delta L over L, for example, for one-dimensional deformation. That is usually dimensionless, as you can see here. So it's always dimensionless. Now, when we start applying a force with ever increasing amplitude, magnitude, as you can see here, the object is going to show first a linear response to the force. So the length of the object, for example, in one-dimensional case, will be increasing linearly. And if I go back to zero force, I will see that this is a reversible behavior, and the object deformation can be reversed back easily by removing the applied stress. This is called elastic behavior. On the other hand, beyond a certain limit, we see that even if we remove the force, we cannot go back to the original condition of the object. The deformation, the amount of deformation that we get, has an irreversible component. That's called plastic deformation. And if we keep increasing the stress that we apply on the force, we see that at some point the object will certainly break. And that's called the breaking point. So there are two important critical points in the stress that we apply. The stress and strain corresponding to this point is basically the limit of the elastic behavior and elastic limit, and then we have an important point where we basically cause a permanent damage on the object. That's the breaking point. Okay, so as we have seen here, the elastic deformation is reversible, the plastic deformation is irreversible. So if you look at the elastic portion of this curve, elastic behavior, we can define an elastic modulus, which is the stress divided by strain. So sigma divided by epsilon. So this is going to work for the linear relationship between stress and strain that's in the elastic regime. Okay, so the one-dimensional case we have talked about, if we clamp this bar on one end and we apply a force on the other hand per unit area, we elongate this object. So we define Young's modulus, which measures the resistance of a solid to change in the length. So the elastic modulus of concern here is Young's modulus, which is the ratio of stress to strain. Now we call this tensile stress to tensile strain. So tensile means it's acting in such a way that it's going to increase the length, so it's elongating. If we, on the other hand, if we apply a force that's going to push it into the object, so it will cause a deformation in the other direction, that's called compressive stress. So tensile stress and tensile strain will correspond to this scenario. If you apply the force in this direction and the object shrinks as a result, we call that compressive. Okay, so the tensile stress, well, as usual, it's the same stress, force per unit area. The tensile strain for this one-dimensional deformation is delta L divided by the initial length of the object. Now we have a variation of this. Let's say that we're talking about a book that is placed on a horizontal table and we apply a force only on one plane of the book. That's the front page of the book, the cover. So if we apply a force in this direction, the bottom of the book is subject to static friction that's coming from the contact with the horizontal table. And as a result, we see a deformation in the shape of the object. So this static friction will be opposing the applied force. It will be equal to minus F if the object does not move. So before the object starts moving, what we see is that the top plane will move a distance delta x in the direction of the force, and h is the distance between the top plane and bottom plane. So we have a force couple here, and we see that one plane is moving with respect to the other plane by an amount delta x. So this is called shear stress. So shear stress is the force we apply per unit area of this plane. So the shear stress causes the top face of the block to move to the right relative to the bottom. So that's basically what we can see in this scenario. So for this deformation, we define shear modulus, which measures the resistance to motion of the planes within a solid parallel to each other. So that is this scenario here. We have a force couple. And the force per unit area of that plane is the shear stress, and shear strain is the relative motion of these two planes, the amount of the displacement of the relative displacement of the two planes, delta x, divided by the distance between the planes, which is h. So delta x divided by h is the shear strain. Now, we can also change the pressure that is being applied on an object. So what is the pressure? It's the force per unit area. So let's say that we have this object placed in the atmosphere. We have atmospheric pressure. There is a force being applied from all sides. And if this is a cubic object, force per area, the pressure is the same on all sides. Then we can say that if we increase the pressure, for example, if we insert it into some if we increase the amount of gas in the room, if we put it into vacuum, for example, we decrease the pressure, etc., we may see a deformation in the shape of this object. So the initial volume of the object can be increased or decreased by an amount delta V. So the bulk modulus is, for this scenario, measures the resistance of the object to change in volume. So this measures the resistance in change in volume. It's the volume stress divided by volume strain. So the object is in equilibrium under a certain pressure. Then we change the force per unit area. So we have delta F over A, which causes a change in the volume, delta V over V initial. For bulk modulus, we have minus delta P divided by delta V over V initial. And why is that? Because if you increase the pressure on all sides of the object, you typically see that the volume will decrease. So because we will get a negative value for the ratio, we put a minus sign here to define this constant for the object to be a positive number. Now, 1 over bulk modulus is called compressibility. So that also measures the same thing. Basically, if the object has a high compressibility, so you can see that delta V over V initial is minus delta P over B, so minus compressibility times delta P. So delta V will be high for a high compressibility, okay? So for example, if you immerse this object in a fluid, you will change the pressure on the object. Now, we have two important remarks here. These definitions, Young's modulus, shear modulus, and bulk modulus, work very well for solids. For liquids, we don't talk about Young's modulus or shear modulus because they simply flow, but bulk modulus is defined. We can change the pressure on a fluid. Number two, the maximum stress that can be applied before breaking is called tensile, compressive, or shear strength. Depends on which scenario we're talking about. So that's basically this maximum stress we can apply here. And after that point, we have permanent damage in the sample. It breaks. Okay, a good example is concrete. Concrete has a compressive strength of 20 times 10 to 6 newtons per meter square. It has a tensile strength of 2 times 10 to 6 newtons per meter square. So it is basically more difficult to break concrete when we apply compressive strength. But if we try to elongate concrete, we apply a force that is basically trying to increase its length. For a concrete bar, for example, it breaks rather easily. So columns of concrete can support high loads, but horizontal beams tend to break because they cannot sustain very high tensile stresses. Okay, so here's an example. Squeezing a brass sphere. A solid brass sphere is initially surrounded by air, and the air pressure exerted on it is 1 times 10 to 5 newtons per meter square. That is basically the atmospheric pressure. 1 Pascal is 1 times 10 to 5 newtons per meter square. Okay, the sphere is lowered into the ocean to a depth where the pressure is 2 times 10 to 7 newtons per meter square. The volume of the sphere in air is 0.5 meter cube. By how much does this volume change once the sphere is submerged into the ocean? Okay. So, the pressure in the air we know to be 1 times 10 to 5 newtons per meter square, or 1 times 10 to 5 pascals. The pressure in the ocean is 2.0 times 10 to 7 newtons per meter square. We have the initial volume 0.5 meter cube. We want to know the volume in the ocean. And we know that this is brass. So we know that it's a brass, solid brass sphere. Okay. Now, the bulk modulus was defined as minus the change in pressure, delta P, divided by delta V over V initial. So with that, we have the change in pressure, delta P, equals minus bulk modulus, delta V over V initial. So this tells us that delta V, which is V final minus V initial, will be given by, so let's call this V initial V0. Okay, so this is the initial volume V0. Minus V0 delta P divided by the bulk modulus will be equal to delta V, V final minus V initial. So plus V initial is equal to V final. So V final minus V initial, if we take this to the right hand side, is delta V. Delta V is minus V0 delta P over the bulk modulus. So you can see that the final volume will be equal to minus initial volume 0.5, change in pressure 2 10 to 7 minus 1 10 to 5 divided by the bulk modulus. Now, what is the bulk modulus of brass? We have to look up this value in a table. So typical values for elastic moduli for brass, this Young's modulus, shear modulus, bulk modulus, we see that it's 6.1 10 to 10 newtons per meter square. So it is 6.1 times 10 to 10 plus the initial volume 0.5. So we can calculate the final volume, which is the volume in the ocean, to be 0.49984 meter cube. So what have we done on this brass? We have increased the pressure on the brass sphere, and we know the bulk modulus of brass. We can read it from this table, and using the definition of bulk modulus minus delta P over delta V over V0, we can obtain the final volume in the ocean. Now, does it make sense? We increase the pressure, the volume decreases, so it's compressed from all sides, and so the volume decreases by a certain amount. So it seems to make sense.